to the third tutorial in this series on quadratic functions. Now, in the last tutorial, I talked about the discriminant, which is a quantity that you can easily calculate given any quadratic function, and it tells you the nature of the roots. Are there any roots, and if so, do you have one or two? Or in the Scottish curriculum, do you have two equal roots or two distinct roots? In this tutorial, we're going to look at some specific examples and see, well, how do I actually calculate the roots, presuming that there are some? So that's the aim of today's tutorial. So quadratic functions continued, and we are looking at the general form of a quadratic function, which we talked about in the previous tutorial. And talking about roots, these are the values of x for which y equals 0. So these are the values of x for which y equals 0. So to find them, we must solve 0 equals this combination. Or in other words, we have to solve ax squared plus bx plus c equals 0. And this is often called the quadratic equation. So it might be confusing sometimes when you're hearing terms like quadratic function, quadratic equation. Quadratic function is this. It's really an operation that you do for any value of x you wish that maps out the shape of a curve, which we call a parabola. The quadratic equation usually means this equation where we're setting the right hand side here, the function, to 0 and asking for which values of x is y 0, and those values of x are what we call the roots. So let me write down the general solution to this equation, which I'm sure you'll have seen at school, and it's often met with gasps of terror from young people. We had to memorize it, I remember, very strictly. The solutions of this equation are given by the following, and I will probably never forget this until my last breath, given the rigor with which it was drilled into us. Minus b plus or minus the square root of b squared minus 4ac all over 2a. That is the general solution of the quadratic equation. Now I will prove that this is true to you in the final tutorial in this series, which, as I mentioned in the last tutorial, is sort of an optional extra. It goes a bit beyond the level that you would need at this particular sort of age range of maths. But for those who might be interested to see where things come from, it's actually not that hard to derive this from here. So I'll be happy to do that later on. But for now, let's just take it as read that this gives you the solution to the quadratic equation. And let's see straight away how this connects to the discriminant. Because look, under the square root is our discriminant. Now we learned that if the discriminant was positive, that we would have two distinct roots. And we see that's true. If the discriminant is positive, its square root will just be some number, and we have to either add or subtract that number from negative b. So there'll be two different solutions here. We also learned if the discriminant is 0, that we have one solution, or again, I have to keep saying this, in Scotland, two equal roots. Well, if the discriminant is 0, the square root of 0 is 0, and so we actually just have one solution, which is negative b over 2a, and that will be the single value of x where the parabola just touches the x-axis. Now we also learned if the discriminant is negative, then there are no real roots. And you see, if the discriminant is negative, then this solution says, oh, just take the square root of this negative number. And at this level of maths, we are simply unable to countenance taking the square root of a negative number, and so we will say there are no solutions. More formally speaking, there are no real solutions. So this formula is quite nice because it connects beautifully with the idea of the discriminant. All of that makes sense. So let's see it in action. Let's do an example. Let's look at y equals x squared, take away 2x, take away 8. So there is a nice looking quadratic function. Let's say that we want to calculate the roots. Let's use the formula. So to find the roots, we have to set the quadratic function to 0. I can read off the values of a, b, and c. Now, one important point, when you see something like x squared and you say, well, what's the value of a? The value of a is implicitly 1. There's an implicit value of 1 there, multiplying x squared. It's a convention of algebra that if a variable is multiplied by 1, we don't write the 1. But if it's multiplied by any other number, of course, we then write that number explicitly. So here, a is 1, b is the number multiplying x, it's negative 2, and c is just the constant term that's kind of loitering, probably a ne'er-do-well, loitering around, it's negative 8. C is negative 8. And let's just plug it all in. So x will be the negative of b. Well, b is negative 2, so the negative of b will be 2, plus or minus the square root of b squared. Well, negative 2 squared is 4. And then take away 4 times 1 times negative 8. So we have to be very careful here to get our signs right. We have negative 8 all over 2 times a. 2 times 1 is 2. So this is 2 plus or minus the square root of, let's see, 4 times 1 times negative 8 is negative 32, times negative 1 is plus 32, plus 4 is 36. All over 2. The square root of 36, of course, is 6, so we have 2 plus or minus 6 over 2. So finally then, 2 take away 6 is negative 4, divided by 2 is negative 2, and 2 plus 6 is 8, divided by 2 is 4. So those are the values of the roots that we're able to calculate directly from the quadratic formula. We see that had we calculated the discriminant for this, we would have got the value 36, because that's b squared minus 4ac. 36 is greater than 0, so we would have known there would be 2 distinct roots for this problem. Now, there are many cases, and this is one, where you can actually do a little bit faster to get the roots, and that is by factorizing. Now, when I say there are many cases, what I mean really is that in exams there will be many cases, because if I write down just random values of a, b, and c, there's no way that I'll be able to factorize, and I'll have to use this quadratic formula. But in exams, often they give you quadratic functions where you can actually factorize. What I mean by that is, if we remember the tutorial in the algebra series about taking a trinomial, can we write that as the product of 2 brackets? Well, let's have a look at this one. We have x and x. That gives x squared. This number is negative, and that tells us that we're going to have x plus something and x take away something. And then we just have to look at products of 8. Well, 8 is either 9 times 1. 8 is either 8 times 1. I apologize, that was really dumb. 8 is either 8 times 1 or it is 4 times 2. But we need to somehow use those two factors to finagle 2 here as the difference. So it's going to be 4 and 2. We want to write them such that we get negative 2x. So I'm going to have to put my 4 here and my 2 there. And you see I have x squared, take away 4x plus 2x is negative 2x, and I have negative 8. So in this case, I can write the quadratic function as a product of two factors. And if I set this to 0 for the roots, then either x plus 2 is 0 or x minus 2 is 0. Sorry, x minus 4 is 0. So either of these two brackets vanishes such that the product will be 0. And you see, I get the solutions that x is either negative 2 or x is equal to 4. So this is a nice example where we see that we could have spotted a factorization and gotten the roots very, very quickly. Alternatively, if we can't spot the factorization, or if it doesn't exist in a simple way, we can just use the quadratic formula. You can always use this, assuming the discriminant is greater than or equal to 0, and you will just find your way to the roots. Let's just sketch this, actually, just a little sketch, just to make contact with some of the earlier concepts. A is 1, so we know A is positive, so we have a valley-shaped parabola. We know the values of the roots. 1 is at negative 2, and 1 is at 4. So there are our roots. So the curve will pass through those values. Now, do you remember that I said that the axis of symmetry, the mirror, point midway between the roots? And the point midway between these roots is actually x equals 1, because that is 3 away from negative 2 and 3 away from 4. So for this particular quadratic function, just knowing the roots, we can locate the axis of symmetry, or the mirror, and just sort of sketch this function. So there it is. And you can even work out what the minimum is here. It occurs at x equals 1. If we set x equal to 1 in the quadratic function, we have 1, take away 2, take away 8, which will be negative 9. So this point here is 1, negative 9. Okay, and there's the parabola. So if there are roots, once you know them, you can pretty much assemble the information of the axis of symmetry, the turning point, and make a pretty good sketch of the parabola. Let's just do one more example where we can't factorize. Okay, so let's imagine we have an example. I've prepared one which I know I can't factorize, so it's 4x squared plus 3x take away 5. So I can't factorize this one, at least not using some simple integers. But no fear, we can still use the quadratic formula. Let's just identify A, B, and C. So A is 4, B is 3, and C is negative 5. Let's just work out by hand what B squared take away 4AC is. That's the discriminant. Presumably, because we're being asked to find the roots, it is going to be greater than or equal to 0, but we can just check. And we need this value anyway when we use this formula. So B squared is 3 squared is 9. Take away 4 times A, which is 4, times C, which is negative 5. If C is negative, always be careful with signs here. You know, I in a previous tutorial, I called these brackets biohazard containers around something toxic. Negative numbers have the potential to cause you terrible headaches. Just treat them carefully and then they'll treat you okay. It's something like this. Put them in brackets so you know there's a negative number here lurking, so that when you work this out, you'll realize that you have negative times negative is positive. So we have 9 plus, because negative times negative is positive, it's 80. So our discriminant has the value 89, which is positive, so that's fine. There'll be 2 distinct roots here. And having calculated this, we can use the quadratic formula. X is minus b, so that's negative 3, plus or minus the square root of the discriminant, 89, divided by 2 times a. A is 4, so 2 times a is 8. So in this case, we need to get the calculator into action. And we take 89 square root. If I take the positive form, then I need to add that to negative 3. And then I divide by 8. And I see that I have one root is at 0.804 ... The other root comes from taking the square root of 89, putting a negative sign, and then taking that from negative 3, okay? Well, with the negative sign, then adding that to negative 3. And then divide by 8, and we have negative 1.554 ... So those would be the 2 roots of that that particular quadratic function. You know, we could even try, why not, just to do a quick little sketch of that. We know it's going to be a valley-shaped parabola because a is positive. And let's see, one root is at 0.8. So if I say that this is 1 and 2, negative 1, negative 2, 0.8 would be sort of there. And the other root's at negative 1.55, so it'd be somewhere around here, okay? And if I just calculate the midpoint of those 2 roots, it tells me what the axis of symmetry is. So if I add the 2 roots together and divide by 2, I get negative 0.375, so the midpoint will be at negative sort of 0.4 roughly speaking, and here's our parabola. Okay, and if we wanted to, we could take this midpoint value and plug it in to get the value of the turning point here, but I'm not going to worry about that because that's a bit too much information, I think, for our purposes. So, just to recap then, quadratic function has a general solution for the roots given by this equation here. The roots will be real, namely for our purposes they'll exist if this discriminant under the square root is greater than or equal to 0. We did an example where we could just use the quadratic formula to find the roots. It happened to be an example where we could also factorize the quadratic function and use algebraic methods to find the roots as an alternative method, and satisfyingly we got the same answers. We were able to sketch that quadratic function. We could locate the axis of symmetry as the midpoint of these 2 roots. And then we looked at another example where the coefficients a, b and c were such that there are roots, but we can't actually work them out by factorization. We just use the quadratic formula, work out the discriminant, take its square root plus or minus from negative b and so on, and we found the values of the roots. So I hope that's been helpful about finding roots. Practice is the key, lots of examples. You can make up examples for yourself, just take any old values of a, b and c, work out the discriminant. If it's positive, there will be 2 roots. Use the formula to work out where they are. Hours of fun. And that's fine. I'll see you for the next tutorial when we will be using a very different and beautiful method to investigate quadratic functions, and I'll see you then.